All right, we're going to pick up where we left off on our 4.2 notes. So let's just get right into it. So the next thing just I want to mention here is domain and range of the sine and cosine functions. Now, we are going to graph these functions and it'll make a little more sense then, but still it's something we can introduce now and keep in the back of our minds. So really what's happening when we're graphing sine, cosine, and all of our trig functions, what's happening is we're graphing, think about if we had a particle here, we're mapping its progress around the unit circle. So it's just constantly going around and around and around. It's called a periodic function, something that repeats all the time. I'm going to have a note about that here in just a second. So when we think about its domain and range, right, domain being all the x values, we can go around multiple times, okay? And the x values are the values that we can plug in because of sine being, whenever we're taking sine of values, we're taking sine of degrees or radians of angles, right? And this number can continue to grow and grow and grow. And we can go both in the positive direction and the negative direction. Now our range, so the y values we get, so the result of us taking sine of an angle can only be the y coordinates, right, of our unit circle, which is 1 and -1. So the point I'm trying to make here is the domain of the sine and cosine functions is going to be negative to positive infinity, okay? And the range of these functions is -1 to 1, where we can get to -1 and 1. Okay, so I jot that down right now. Again, we're going to look at that a little bit more once we start graphing these functions, but I'm going to have you write that down. If you need to hit pause, make sure you get that written down. Go ahead and do so. Okay. Now, we're just going to kind of build off what we did last time, all right? So this is where we're going to use our unit circle. Now, yes, you can always have this unit circle right next to you, but again, ideally, we can come up with this unit circle without needing this. So here's what I would do. If I'm trying to do this without a unit circle, I'm going to draw this, and I need to figure out pi over 4, which quadrant is that in? Well, here I know that this is 0 radians, right? This is pi over 2 radians, and pi over 4 is smaller than pi over 2. So we're in quadrant 1, so we only need to draw one quadrant. In fact, if we remember back to our unit circle, and this is why you can look at it, okay, it's only halfway there, right? Pi over 4 is right in between pi over 2 and 0. So pi over 4 is our radian measure. Now we're going to label these coordinates. This is that middle coordinate. Okay, so all middle coordinates are √2 over 2, √2 over 2. This is the goal, is for us to be able to build this for every single angle that's on the unit circle. Now, if we have this, right now we can go ahead and find the value of our sine, cosine, and tangent of pi over 4. So sine of pi over 4 is equal to the y coordinate there, which is √2 over 2. And cosine of pi over 4 is equal to the x coordinate, which is also √2 over 2. Okay, now we get to tangent. Almost always with tangent, we're going to have to do a little more work. So tangent of pi over 4 is y over x, which is √2 over 2 divided by √2 over 2. Well, what's anything divided by itself? Wouldn't you all agree that anything divided by itself is 1? Well, let's make sure of that by actually doing this dividing. √2 over 2 times the reciprocal of √2 over 2. Well, I have √2 divided by √2, which is 1, 2 divided by 2, which is also 1, and therefore it is 1. If you still don't believe me, grab a calculator and try it on your own. See what you come up with, okay? So this is, again, our goal. Can we draw the angle? Remember the coordinates. It might even help that we draw in the other coordinates to help us with that. Okay, that's something we can do. Okay, where this would be pi over 6, which would be √3 over 2, comma 1/2. This would be pi over 3, which would be 1/2 √3 over 2. If you can make this like I did right now, you can get any value on the unit circle from here. Okay, this is all that you need, because then we'll just reflect. Okay, and then again, we can just continue to reflect on all our other quadrants as well. Right, let's keep on moving here. Really, we're just doing more things like this, but we're going to also introduce some trig identities. That's what these are right here. This is going to be the part that we don't need to necessarily remember. Now, it's really just a result of all the things we did with our unit circle and the trig functions and their values. So I would jot these down, but unlike an assessment, I'm going to give these to you. So don't worry about memorizing these too much. Okay, but if we have these, sometimes we can find values of trig functions a little bit quicker. Okay, so these are what's called the reciprocal identities. Okay, where sine of t is equal to 1 over cosecant of t. We can take some time to prove that. It's going to be proved just like how I talked about how we got sine of t to equal y, right? This would be like 1 over y. And if we did the reciprocal, we're going to get y, which is what sine of t is equal to. Okay, so that's a really quick version to explain it, right? So if you need to pause, write those down, definitely do so. Quotient identities, these ones do get used a little more frequent, especially that tangent one, right? Tangent of t is equal to sine of t over cosine of t. Well, why is that? Well, sine of t is y, cosine of t is x, right? So, and tangent is equal to y over x, right? All of these are derived from the identities or the 6 trig functions that I already provided for you. Okay, so let's see how these work out and how we can use these. And again, if you need to hit pause to write them down, go back and do so. It says, given that sine of t equals 2/5 and cosine of t equals root 21 over 5, find the values of the 4 remaining trig functions. So we need to find tangent of t, cotangent of t, secant of t, and cosecant of t. Well, let's look at our values up here. Well, actually, let's start with our reciprocal. Okay, since we know sine and cosine, tangent of t is equal to sine of t divided by cosine of t, which is cosine of t is root 21 over 5. Let's try that again. Sine of t is 2 over 5, and cosine of t is root 21 over 5. Just like all the ones we were doing yesterday, we're now going to have to copy the top, 2/5, and multiply by the reciprocal, which is 5 over root 21. 5's divide out, making this 2 over root 21. We do not want square root in our denominator, so we're going to multiply by root 21 over root 21, which is 2 root 21 over 21. Okay, so really all this is another way to find these values here. We are going to do some things with these identities. You might be like, well, can we just call this x and call that y and just do what we were doing before? Of course. Okay, but I want us to get familiar with these identities as well, because we're going to do quite a bit with those down the road, right? So cotangent of t is just the opposite, right? I'll go ahead and give us a little more room. Cotangent of t is cosine of t divided by sine of t, which in this case is root 21 over 5 divided by 2 over 5. And just like before, we're going to have to do the division between the fractions. So root 21 divided by 5 times the reciprocal of 5 halves. 5's divide out, and this is just simply root 21 over 2. Okay, not too bad at all. All right, secant. Let's go back and look at what one of our reciprocal identities tells us that it is. Secant of t is 1 over cosine of t. So 1 over cosine of t, same thing as 1 over x, is 1 over root 21 divided by 5. We need to multiply by the reciprocal, so 1 over 5 root 21, which is 5 over root 21. We need to multiply by root 21 over root 21, giving us 5 root 21 over 21. Okay, so really the same math or algebra steps as we were doing yesterday, but now just approaching the problem a little bit differently. All right, I think we get the hang of it. Actually, let's just go ahead and do cosecant as well. Cosecant of t is 1 over sine of t. Luckily, we don't have any square roots here, so this will go a little bit quicker. So that's 1 over 2/5, which means we're going to take 1 and multiply it by the reciprocal, which is 5 halves, and that's our value, is 5 halves. So cosine of t is equal to 5 halves. Okay, let's keep on moving. couple other identities. Okay, and I know I'm throwing a lot out at you. You don't need to worry about memorizing the identities, just knowing how to use them. Okay, so this is the equation of the unit circle, x squared plus y squared equals 1. And I did show this to you on your first day of the unit circle. Now, if we think about, since cosine of t is equal to x, couldn't we call this x squared, cosine of t squared? Yes. And since sine of t is equal to y, couldn't we call this sine of t squared? Yes. Coming up with a really important identity called the Pythagorean identities of cosine squared plus sine squared equals 1. Now, typically, we're going to write it as sine squared plus cosine squared equals 1, although when we're talking about addition, the order doesn't matter. Okay, so that's where that comes from. So I'm going to have you jot these down as well. Again, hit pause if you need to. This one we use quite often, okay, not only in this class, but in future classes as well, right? And it's going to be really helpful for finding some values. All right, so let's see what else we got. Using a Pythagorean identity. It says, given that sine of t equals 3/5, and that our value of t is between 0 and pi over 2, meaning it's in the first quadrant. So quadrant 1, and I'd write that down, and might as well jot that down. Find the value of cosine of t using a trig identity. Let's use this Pythagorean identity. So we're going to start with sine squared of t plus cosine squared of t equals 1. Now, one thing I want to mention real quick, just because this is written, I wouldn't say funny, but a little bit different. See how up here we just squared cosine of t and it's outside the parentheses? This is the same thing as writing it like that. So sometimes we just put the square after the cosine, just so that we're not confusing it with squaring just the value of t. Okay, that's why that square goes there. So it's squaring the whole thing, okay, not just the value of t. Really important distinction there, that we would find the value of cosine of t first and square that, not just square t and then take the cosine. Okay, so that more helps with our order of operations here. All right, so we know the value of sine of t, which is 3/5. So really what we have here is 3/5 squared. That's taken over for the sine of t squared. And that's going to allow us to find cosine of t. Now, yeah, let's actually keep going with this. All right, so 3/5 squared, this really is like 3 squared divided by 5 squared, which is 9 divided by 25, plus cosine squared of t equals 1. So we want to get cosine squared of t by itself, just like if we had an x squared in here, it's the same idea, and then we're going to take the square root of both sides. So I'm going to minus 9 over 25, so 1 minus 9 over 25. Well, this needs to be a common denominator, so let's change this to be 25 over 25. So 25 minus 9 means that cosine squared of t is equal to 16/25. Right? 25 minus 9 keeps the denominator the same. So our value of cosine of t, we can get cosine by itself by square rooting. That gets rid of us squaring cosine. And so cosine of t is equal to the square root of 16 over 25, which we can take the square root of the numerator and denominator separately, giving us 4/5. So all that work getting us to say that cosine of t is equal to 4/5 in this case. Okay. This proves to not really be too relevant here. That just means that we wouldn't need to think about, okay, what happens if we did more than one revolution? All right, so that didn't matter too much. All right, well, there's your first look at using a Pythagorean identity. Again, these things just take practice, okay? All right, one thing I mentioned earlier is periodic functions, okay? And that's what all these trig functions are. They're functions that repeat, and that's what this is saying. Certain patterns in nature repeat again and again. For example, the ocean level at a beach varies from low tide to high tide and then back to low tide approximately every 12 hours. Okay, it can be modeled by trig functions. That's why trig functions show up all over the place. So there's a lot on here. I'm not going to have you write down all of this, but basically a periodic function is one that exists where it repeats. Okay, that's a fancy way of saying if we add some value of p, we get to the same value eventually later. Okay, so don't worry about this part up here. What we need to know is that sine and cosine are periodic functions that repeat every 2 pi. Okay, so let's just write this down. These right here. And these are periodic properties of sine and cosine. Okay, and what this means is they repeat values every time we go all the way around the unit circle, which is 2 pi. Okay, we've seen that before, right? When we wrote like coterminal angles, right? We had something that was, we're finding the same radian measure as, let's say, 5 pi over 2. Well, 5 pi over 2 is the same thing as pi over 2. Okay, so it just means that we can get the same values of sine of t by adding 2 pi, and that could go on forever and ever and ever. Okay, now similarly, tangent and cotangent are also periodic functions. However, they are going to repeat every pi amount as opposed to 2 pi. Okay, so I'm going to jot that down as well. So here's why this is useful. And again, if you need to hit pause to write any of these 2 things down, definitely do so. This is useful because if we want to find the value of sine of 9 pi over 4, and you grab your unit circle, you're like, well, there's no 9 pi over 4 here. Well, let's figure out what is 9 pi over 4 if we take away that one rotation, that 2 pi. What does that get us to? So we can do kind of this fraction decomposition where we take 9 pi over 4 and we break it down into something smaller. Well, 9 divided by 4 is really 2 1/4. So really what's happening here is we have sine of pi over 4 plus 8 pi over 4, right? We can check this. Pi plus 8 pi is 9 pi, keep the common denominator is 4, which means that this is equal to sine of pi over 4. So sine of pi over 4, and this time we'll just go ahead and check our unit circle rather than drawing it, although drawing it's always a good exercise. If I go to pi over 4, sine is the y coordinate, which is root 2 over 2. That's also the x coordinate. So what this means is sine of 9 pi over 4 is also equal to root 2 over 2. Okay, we get to the same values as sine of pi over 4 and sine of 9 pi over 4, right? This one we're going to treat a little bit differently because we skipped something called even and odd properties. So we're going to go ahead and get this to be within, since it's tangent, we want it to be in less than 1 pi. We'll leave it as negative, okay? And we'll again bring that unit circle out. This one's a little bit trickier. So again, let's break this down. We're going to call this negative pi over 4. And we're subtracting away 4 pi over 4. Right? So really, I'm just finding a way, how can I get rid of 1 pi? And 1 pi here, and again, why is it 1 pi as opposed to 2 pi? Because of the periodic properties of tangent and cotangent. They repeat every pi, okay? So all I'm doing is saying, okay, if I subtract away 1 pi, which in this case would be negative 4 pi over 4, that's what this is here. What's left over? 1 more pi over 4, right? And again, we can check this. It might take some writing down and checking before you start to get these right. So negative 1 pi minus 4 pi is negative 5 pi over our denominator of 4. So we like this. This means that this is equal to tangent of just simply negative pi over 4. Now, since we didn't talk about even or odd functions, we can go to our unit circle and remember that negative radians or negative degrees tell us to go in the opposite direction. Okay, so instead of us going counterclockwise, now we're going to go clockwise. So 1 pi over 4, right? It was just a quarter turn up. Now we're going to go a quarter turn down, bring us to these values down here. Root 2 over 2 is x, negative root 2 over 2 is y. Remember that tangent is y over x. So in this case, y is negative root 2 over 2, and we're dividing it by x, which is also root 2 over 2. When we do our division here, it's negative root 2 over 2 times the reciprocal of 2 over root 2. And what's nice here is everything divides out, except for that negative. They divide out because they equal 1. So tangent of negative pi over 4 is negative 1, which means that tangent of negative 5 pi over 4 is negative 1 as well. That one's a little bit trickier. Again, it's going to take some practice before we get the hang of it. Math Excel will show you a different property if you hit the example here. I'm going to encourage you to try to do it this way because I'm, again, trying to limit the amount of things we need to remember. And already I gave you a ton of properties, right? We don't need a couple more. Okay, we got one last thing that I want to do, and then we'll be all done. So the only other thing I want to mention is, and you know what, we're not going to skip this last one, so we're about done, is this can happen more than one revolution. So this is saying that it can repeat more than just one time around. So 2 pi n representing that we're taking more than one trip around the unit circle. So it could be 2 trips around, 3 trips around, 4 trips around, etc. So I don't think you need to write these down again. I think we kind of have the idea by writing down the other values. Okay. I don't want to do calculator stuff today, so we're going to skip this and the video right there. Thanks for watching. Have a great rest of your day.